In the previous video on current electricity, we had obtained the expression for the drift speed of electrons within a conductor, that being equal to Vd, which is equal to E times of the E being the charge of the electron times the potential difference across the conductor that has been provided, that is V, and divided by mass of each electron and the length of the conductor considered, that is L, times of tau, where tau is the relaxation time which gives us the average of all the successive collisions, time for each successive collision between those electrons. This being the magnitude of the drift velocity. Now this drift velocity that we had obtained, uh, we were to obtain a relation of this drift speed with the current that is established within the conductor due to the flow of charge, in this case the charge being the charge of electrons. And so let us consider once again a conductor. This again is a segment of the entire length of the wire that we can consider, this being a small segment of it, and the segment supposedly in this case has a length which is equal to the drift speed, which means that as an electron flows from one end to the other, which I'm representing right now with those dashed lines. So as an electron flows from one end, let the end be B, to the first end being A, where A is subjected to a higher potential and B is subjected to a lower potential or the negative potential. So as the electron flows due to the influence of the field, so this electron would take only 1 second, because its drift speed is Vd, which is equal to the length of the given conductor. So because we know that speed is equal to the distance, here the distance is the length of the conductor, suppose it was L, and if I take t as 1 second, so obviously here we have L is equal to Vd, which is what I have considered over here. Now this is a simple relation of speed and distance with time being equal to unit value. Now from this, what we can say is that it's not only a single electron which is going to flow, there will be a whole bunch of them. In fact, we can always compare it with the Avogadro's number, but let us say that we have a value n, small n, over here, where n is the number of electrons per unit volume. N is the number of electrons per unit volume of the given conductor. Now if we are considering n be the number of electrons per unit volume, then obviously the volume of this conductor, let us say this conductor has once again an area of cross section A. So the volume of the conductor we have considered in this case is equal to the area of cross section multiplied with the drift speed, A times of Vd. And with that volume we can now calculate the total number of electrons which will flow from one end to the other end in the given space of the given segment of the conductor. So let n, capital N, be the total number of electrons that are flowing. So that will be equal to this small n that we had, that is number of electrons per unit volume, multiplied with the given volume. So that will give me n equals N times of the volume being A times of Vd, where Vd is obviously the drift speed, and here equal to the length. Now this being the total number of electrons, so what is the total amount of charge that is flowing? So the total amount of charge Q, as per the quantization principle, Q is equal to N times of E, where N is the total number of electrons that we have determined already, and E is the charge carried by each electron. So that is equal to, for N we can write N A V D, and for E we already have E over there, so NaVd times of E. Rearranging it, it's easier to remember. NeAVd you can remember in any sense you want to. So this being the value of charge that is flowing. Now how much is the amount of time that it's taking? As discussed, with the length being equal to Vd, this amount of charge will obviously flow across the given section in 1 second. And what is the amount of charge that is flowing across a conductor in 1 second? The charge flowing, that is the charge flowing per unit time, and obviously that is equal to the current. So the current over here is Q by 1 second, which is the time in this case that we had already taken over here. So Q by 1 second, that means NEA times of Vd is what we have the relation of current with drift speed. Now if you observe this thing closely, you have NEA, they are constant quantities or constant terms when we are considering a known conductor. Let us suppose say a copper wire. Now copper, in case of copper, we have 63.5 grams of copper carrying Avogadro's number of atoms, and each atom may contribute a single electron. So we have as many number of electrons, that is Avogadro's number of electrons available for conduction for every 63.5 grams. So the value of N remains fixed for a given type of conductor. E being the charge of electron obviously remains constant, and A being the area of cross section maintained uniformly throughout the wire also remains constant. So now these three terms that I have written over there, they are constant. So only thing that may change is the drift speed, which is given by the relation that is above over there that I have ticked right now. So I equals NeAVd is giving me I to be proportional to the drift speed, directly varying with respect to the drift speed. That means the current increases with the increase in the drift speed of the electrons. Now drift speed, as you know, was of the order of 10 to the power minus 4. So but we do not have that magnitude of current. Obviously we cannot have that magnitude of current because the 10 to the power 4 is compensated by this, 10 to the power minus 4 is compensated by this multiplication that we have over there that I am just circling right now, that is N times of E. N is obviously when you take Avogadro's number 10 to the power 23 and plus 23 of course, and E being 10 to the power minus 19. So you have a plus 4 over there and a minus 4 in drift speed, which is almost equal to 10 to the power 0 or 1 or somewhere in that range. So you have a proper value of current which is measurable by the ammeter. This is a usual example that we have with us. With this value of, or this relation of current and drift speed, we can just move a bit further and establish a few more relations. Now, as we know that the drift speed has been written explicitly right at the top of this page, we can just put that value over there and see for ourselves if we have some new relations available to us. So NEA can remain as such in the above equation, and for Vd I can use E times of the potential difference V divided by me, that is the mass of the electron, times the length. Now this length is some other length that of the conductor that I'm considering, the general length of the conductor, although it's Vd over here, but we are considering a general formula right now, so you need not confuse with that. So in this case I have I to be equal to, the e's can get multiplied, ne square, and we'll write the a later. We have ne square, we can put the tau, that is relaxation time, over there, divided by me, and we can keep this in bracket. We'll see for ourselves why I've done that, and we can put the a and l separately, and then outside that square bracket that I've just constructed, I can keep a v, that is the potential difference. Now this entire term that I have just marked in curls, that is what we call as conductance, usually represented by capital K, which is the property of the conductor, which is the conductance is the property of a conductor which allows it to conduct the current. It is dependent on few factors that you can see, all those values, the whole range of symbols that are available there, that is n e square tau divided by me and a divided by l. Now the bracketed term, the curved braces that I have considered there, that is ne square tau divided by me. Now in that, if I say for a given wire, taking again the example of copper wire, we have a fixed value of n, that is number of electrons per unit volume, or the number density of the electrons. E is also constant, me, that is the mass of the electron, is also constant, times of the relaxation time, which is a constant for a given condition of temperature. Say suppose a room, we are operating at room temperature, so the general room temperature range, the tau, that is the relaxation time, remains almost the same, so that is also a constant. Apart from that, we have A divided by L, which tells us that conductance is dependent on the area of cross section available and the length. So the greater the area of cross section, obviously the greater is the conductance, because the electrons get better space to move along the conductor, and the lesser the length, obviously the quicker they can travel from one end to other end. If the length is lessened, then obviously they can travel easily and quickly from one end to the other end, so that case the conductance increases with the shortening of length. Now this brings us to a certain law, which is popularly the Ohm's law. Now Ohm's law is obviously telling us in this case that I is proportional to the potential difference with all the, now the area of cross section and the length for a given conductor are fixed, so obviously that entire square bracketed term, that is the conductance, under a given condition is fixed for a conducting wire. Now that remaining fixed, I is proportional to the potential difference, and where is the potential difference? Applied across the ends of a given conducting wire. So that means, which is the Ohm's law, of course, and what does the Ohm's law tell us? It states that the current that flows across a conductor is directly proportional to the potential difference applied across the ends of the conductor. But there's a condition over there, because I mentioned that the relaxation time part, that has to be considered. The relaxation time may change because of the relaxation time is obtained obviously because of the collisions between the electrons, and that may change if the collisions become quicker or are sluggish. Now the collisions obviously will get quicker if the electrons are excited to a higher energy with the increase in temperature. So that is what we say, that for Ohm's law the temperature and other physical conditions, they must remain constant. So the temperature with temperature and other physical conditions being like the area of cross section, the length, the pressure, and everything with temperature and other physical conditions, using shorthand notation. So other physical conditions remaining constant, we have the Ohm's law, which states that the the current flowing through a conductor is directly proportional to the potential difference across its ends. Now obviously the electrons, although they flow, they have a conductance for the given conductor, but obviously they are hindered or restricted in their paths because of the collisions, of course. So that hindrance or restriction, or that we commonly consider or tell, is resistance. So that hindrance provided to the flow of electron, or obstruction provided to the flow of electron due to their own collision, own process of collision, is known as resistance. So we have a term called resistance, which is just the opposite of conductance, or opposite meaning reciprocal. So resistance R, represented by the symbol R, is the reciprocal of the conductance in this case that we have obtained. And so the above expression that we have over there is I, that was equal to K times of V, now becomes I equals 1 by R times of V, or we have V is equal to Ri. So that is the popular form of writing the relation between voltage and current across a conductor, with R being the resistance. The unit of resistance is ohms, and obviously the dimension, you can obtain the dimension. The dimension for R in this case is equal to, now the R is equal to V by I. So V has the dimension of energy per unit charge, ml square t to the power minus 2, and per unit charge means at for charge, and there is a current over there, that is A. So we have R to be equal to m L squared t to the power minus 3 a to the power minus 2 is what we have the dimension of resistance. And likewise you can obtain the dimension of conductance, which is just the reverse or the reciprocal of the dimension of resistance, that is m to the power minus 1 L to the power minus 2 t to the power 3 a to the power 2. So, and the obviously the unit of conductance is ohm inverse, popularly called as mho or Siemens. So K has the unit of ohm inverse. Ohm is usually symbolized as the symbol is omega, and from that term omega we have ohm. Omega there at the bottom, I have bottom right corner that I have just sticked right now, and for K we have ohm inverse. So that's it for this video. We will be discussing more on this Ohm's law and resistivity, conductivity, the other terms to follow in the next video. Till then, thank you.